So in the previous videos we sort of discovered what exactly we would mean by a two-pre-sheaf, or more properly by a fibred category. And since stacks can also be called two sheaves, we would now like to discover how exactly we can translate these gluing conditions we already know for sheaves, how we can translate this idea of gluing, or in more proper algebraic geometric terms, of descent to fibred categories. So let's talk about descent data. So first, let's make a bit of a convention about notation. Let C be a site, and let F be a fibred category on C. Let Fi from Ui to U, I and I, be a cover inside our site C. Then we have the maps F of Fi, sort of the pullback maps of the fibred category. But since we would really like to generalize the stuff from sheaves, and in sheaves we always talk about restriction maps, we are also calling them restriction maps. So we just write this as restricted to UI, and we're just omitting these maps. They are always implicit. And the second convention we're going to make is that we can pull back covers by one of the covering maps, so that fiber products of these covers exist, which I guess isn't really a notation convention, but it's very useful and it will usually be the case. So assume UI cross Uj over U, which, when we're talking about covers of topological spaces, is just the intersection of Ui and Uj, as well as other finite fiber products of the Ui exist. And we call them I1 until IL is just the fiber product of UI1 over U until UIL over U. So this is just a notation for sort of finite intersections of these covering sets. And now let's define what we mean by descent data. So again, let C be a site and F be a fibred category on C, given a cover capital German U, UI to U for I and I. Define the category of descent data, DD of the fibred category, and the cover U by, so the objects are going to be, when we did the same thing for sheaves, we had two things. We first had sections on these UI, and secondly we had the property that they are the same on overlaps. Now when we do this for sort of one category step higher, we need to provide isomorphisms. So what we're doing is we're having objects of the Fi, so not sections, because, well, they are not sets, they are categories, the FUI, and we have isomorphisms indexed by two elements of our index set, such that the xi is an object of f of ui, and phi ij maps from xj restricted to uij, so that is what I talked about above. It's the functor restriction to uij, which is the fiber product of ui and uj, applied to the object xj, and maps to xi restricted to uij, and this is an isomorphism. And now we have a restriction on that, such that, and this is usually called the co-cycle condition, we want Fij restricted to Uijk, composed with phi jk restricted to Uijk, composed with phi ki restricted to Uijk, to be the identity on Uijk. Note that phi ki maps from the second thing to the first thing, so it maps from xi to xk, then phi jk maps from xk to xj, and lastly phi ij maps from xj to xi, all of them restricted to Uijk, of course, so this should really be the identity on the object xi restricted to Uijk. Sorry about that. And I guess the second co-cycle condition is that phi ij composed with phi ji is the identity of xi, because this maps from xi to xj and then back to xi. And those conditions together then of course imply that phi ii is also just the identity on xi, well, restricted to Uij. And secondly, what are the morphisms in our category of descent data? Well, our morphisms are given by maps alpha I for I and I. And, well, there's two things to that. Firstly, we need to do something with the objects, and secondly, we need to somehow be compatible with the isomorphisms. So first thing, we have alpha I. Well, of course, the morphisms from one piece of descent data to another piece of descent data. So we have from xi phi ij to yi psi ij. And now, firstly, alpha I is a morphism from xi to yi. They both live in the category f of ui, so that is a well-defined concept. And secondly, they need to behave well with the restrictions. So what do we have? We have xi restricted to uij, we have yi restricted to uij, then we have xj restricted to uij, and we have yj restricted to uij. And what we can now do is we can map using alpha I restricted to uij, we can map with alpha j restricted to uij, and then we have phi ji here, and we have psi ji here. All this needs to commute. In other words, we have alpha j after phi ji equals psi ji after alpha I, which has a nice symmetry to it. One other thing we are defining, again given the cover U of an object U of our site, there is a canonical functor called small dd going from our category f of u to descent data of f given the cover u. And what does this functor do? Our functor dd applied to some object x of f of u is just given by, well, we have descent data. Descent data is given by two things. Firstly, we have f restricted to ui for I and I, so our cover again given as ui to u, So we have X restricted to UI, and for the gluing map we have just the identity of uij for I and j. And our functor of canonical descent data applied to some morphism f from x to y is just given by, well, f restricted to ui for every I and I. So this gives us the canonical descent data for every object in f of u, and now we can start defining what this whole series has been working up towards. Namely, we can start defining a stack. So a fibred category is called firstly a pre-stack if for every cover u of u, the functor small dd, well, I guess of the cover u, is fully faithful, and secondly it is called a stack if our functor is not only fully faithful but also an equivalence of categories. Now, what do I mean by those fancy words? So recall a functor f from C to D is full if for all objects x and y in C the map morphisms in C between x and y to morphisms in D between fx and fy. That just maps f to f of f. If that map is surjective, it is called faithful. If that map is injective, and by that argument it's called fully faithful if it's surjective and injective, i.e. bijective. And lastly, such a functor is called essentially surjective if, well, surjectivity means that for every object in D we can find an object in C such that f maps that object in C to that object in D, except that equality of objects isn't really what we should aim for. We should really aim for isomorphism of objects. So it is essentially surjective if for every object y in D there is an object x in C such that f of x is not equal but isomorphic to y. And finally, a functor is an equivalence of categories if it is fully faithful and essentially surjective, i.e. if it is all of the above. So what does that mean if we apply it to fibred categories? Well, that means a fibred category is a pre-stack if the maps of DD on morphisms are bijective, meaning that we can sort of glue morphisms, or morphisms are uniquely determined by their action on every cover, and conversely, if we have compatible morphisms on a cover, we can glue them to a morphism on the whole, and it's called a stack if, in addition to being able to glue morphisms, we can also glue objects.